Okay, I got a request for number 2 from chapter 21. And so just do a video help to get some background to it, maybe jog some memories since it's been quite some time. So you can see here, rectangular loop shown in this figure is pushed into a magnetic field which points inward. In what direction is the induced current? Okay, so I reworked this. Let's see if I can get that out just for glare purposes. I tried to indicate with the blue arrow which direction the loop is going. Okay. Now the concept that drives it, the EMF, right, is a voltage. If you have a potential difference, which is a voltage, you can drive current. Okay. So if I have an EMF, right, that is impacted by the number of loops, right, the change in phi, which is flux. Okay. Now flux is B times A. Now there's a little bit more to that, but it's the product of the field strength times the area. So you can change flux over time. You can change your flux by increasing the field itself or by increasing the area, all right? So what is happening when I move this loop into the field? So if that were the boundary line of the field, is my flux increasing or decreasing is the question you ask. So it's into the page, and this is how I use it, okay? And what it's doing when I move it in, I'm increasing the amount of field that's in that set area. Or I could think of, here's my area, and then my new area, right? My new area would be this much. So before I had 2 x's, now I've got 3 x's kind of thing. So into the field, and it's increasing. So what I want to do, so this is Faraday's law that says a change in flux, which is your field and your area, or the rate of change of your flux, which is over a time interval, right, gives you an EMF. Now, this negative sign tells you the direction. Lentz's law says the field that's created, right, is going to be offset, essentially, by a current that creates another field. So if I am increasing this way, I have more into it, I have to oppose it, okay? And when I do it with this, that means my current, right, is going counterclockwise, okay? So I want you to, let's read Lentz's law a little bit closer to see if let's see if I've got it up. If we can find Lentz's law on here with my screen. Hopefully I wasn't standing in front of that the whole time. Let's see, chapter 2. Hopefully this isn't taking too long. Let's open that up. Textbook right there. And I'm gonna go up. And Lentz's law. Right here, a current produced by an induced EMF moves in the direction so that the magnetic field created by that current opposes the original change in flux. So I'm going into the page, and now I have more into the page, so I roll towards the page, which means I need to oppose it, so I flip my hand, and I come out of the page, which will give us a counterclockwise current in that loop. I hope that helps. There are plenty of examples that you can work through, right? How they've changed the magnetic field by physically manipulating, right? Moving the loop, decreasing the size of the loop, changing where the magnet is in orientation to the loop, same thing here, and even rotating that loop, okay? And then further down, there's more examples, as if I've got increasing current in that wire, that's going to change the magnetic field around the wire or conductor. So take some shots that give you examples, and they'll confirm A, B, C, and D, increase or decrease. So I hope that helps.